Good afternoon, everyone. I am Wavelength, as he just said. Today's topic is header steganography. We're going to be talking about abusing the IPv6 headers and prefix delegation for data exfiltration. All right, already first fail, sorry. There we go. Okay, so before we dive in, the standard disclaimers for every presentation apply, especially the one about using anything I tell you today for illegal shit. Second, since we have such a wide range of people here with different skills, I'm going to try and cover the whole base and give everybody a bit of information. So we'll have some basic topics and some more advanced stuff. And finally, questions are welcome, but if we can hold them to the end, that'd be really good. So it's a little bit about me. I am a New Orleans area native, moved here in 2012. I've worn many hats throughout my career. Been an IP engineer for some very large internet service providers. So that's how I have a lot of experience with IP version 6. Recently transferred over to cybersecurity. So let's get started. So if you don't know what data exfiltration is, you're like, data exfil what? It's basically just stealing information that we shouldn't have access to as a threat actor. There are a couple of different names for it. We've got data theft, data exportation, and my favorite, data extrusion. There are a couple of different motivations for data exfiltration. The biggest and most popular one is the financial crimes. These are your Equifaxes, your target data breaches. These are geared toward getting your personal information to open credit in your name or to get medical information to commit Medicare and Medicaid fraud. We have industrial and state-sponsored espionage. This is Russia, China, hacking American interests to try and get strategic information, military troop movements, technological information about us. We have hacktivism. This is the WikiLeaks kind of thing where there's a political agenda behind the data theft to expose it to the wider audience of the world. And then we have a few others, intelligence gathering. These are our three-letter agencies. The police trying to get information on groups like Al-Qaeda, ISIS, and the Taliban. So data exfiltration is really old. It's been around as long as there's been adversarial relationships between human beings. If any of you watched old World War II films or the 80s spy movies where the guys are walking around with microfiche cameras, that's these analog methods. So either printing, photocopying, walking and memorizing a document and transcribing it. These all require physical access to the data, so there's a higher risk involved in doing it. You're either going to, you may get caught, imprisoned, shot in the process. Not really fun. Once we moved into the digital age, the sneaker methods appeared. So those of you who are old enough to remember, floppy disks, you walk in, you stick it in the computer, copy, paste, walk out with it. Nobody knows. Nowadays, we use USB sticks. As the internet evolved, the threat model changed and the risk went down. Now we don't have to go to our enemy or adversary and copy the data. We just do it from where we are. So there is no longer that risk of being shot or caught or imprisoned because China and Russia are not going to turn their operatives over to us when they get caught. So there's some obvious protocols. First one being file transfer. The name kind of gives you a hint of what's going on there. We have HTTP and HTTPS, and then we could just simply mail data to and from ourselves, from our victim. In addition to those, we have some more exotic methods. For example, the DNS exfiltration technique is taking data, encoding it, and embedding it in a DNS query that will eventually end up at a DNS server that the threat actor controls, and he will just simply log those transactions and reconstruct the data. ICMP is also embedding data in an ICMP packet. The threat actor would simply ping a host that he controls, log all of those packets, and then reconstruct the data. There is a common thread with all of these. If we look at the OSI model, these protocols tend to cluster around the top of the OSI model. There's a reason for that, but we'll get to that in a sec. But there are risks with using these. If you have firewalls, a threat actor could be detected based on the sessions that he creates through the firewall. A lot of firewalls are logging all of the traffic. Outbound ports or protocols could be blocked. And those failed attempts could trigger alerts that your SOC team is going to notice. There are also IDS, IPS signatures that are capable of detecting a wide array of different data exfiltration techniques. There are just a few snort SIDs there for you guys to look at. SIM correlation rules can detect a threat actor working in a network to do data exfiltration techniques, so he could be discovered that way. And then DLP systems can monitor every one of those protocols we just looked at for exfiltration activity. So why do threat actors use them? Well, first, threat actors are pretty lazy. They're really easy to use those protocols. You've got a wealth of utilities already available. If you're writing custom malware, you have a wealth of libraries available for every language on the planet. There's a mature ecosystem of servers available to receive and send data to. And these protocols all have flow control, so you don't have to sit there and manually worry about your data being lost in transit. They will take care of retransmitting for you. But the biggest reason is that most networks don't block all of the protocols we just looked at. If your average user can get on the network and surf Facebook at lunchtime, you are vulnerable to data exfiltration through HTTP. Second reason we use these higher layer protocols is simply that there's no space the further down you go in the OSI model. If we look at an IP version 4 header, we see a wide array of fields that we could use, but there's just not enough room. Most of them, like our source and destination address fields, we can't really put arbitrary data there. Total length, fragment offset, and header checksum fields, these also can't carry arbitrary data. If we look at the TCP header, we do have some places we could sneak data in. The source port, for example, can carry 2 bytes of data, along with the destination port. The sequence port, or sequence number field, can carry 4 bytes of data, and the acknowledgement number field can also carry 4 bytes. Some of the other fields are calculated fields and so will not carry arbitrary data. Next, the UDP header. Again, just like TCP, we have the source port and destination port that'll also carry 2 bytes. Length and checksum fields are calculated fields and cannot carry arbitrary values. The biggest reason we move to the application layer protocols for data exfiltration is network address translation, or more specifically, network address and port translation. The reason for that is NAT changes parameters at layer 3 and 4. Specifically, the source IP and destination IP, if you were to encode data there, during the translation process, those fields would change and you would lose your data. Source and destination ports also change. We'll see that in a moment. And some firewalls, specifically ASA firewalls, will muck around with the TCP sequence numbers. So end-to-end integrity of your data is not guaranteed. But why do we put up with this? A little historical context. Back in the 80s, IP version 4 was formalized. And when that happened, there were only a few thousand machines connected to the global internet. But by the 90s, it was pretty obvious we had a small problem. The internet was expanding at thousands of hosts per day and growing even faster. Now, IP version 4 gives us 4.3 billion addresses until we take out all the IETF mistakes of reserving wide swaths of space, which reduced it to 3.4 billion addresses. Seems like a lot, right? But if we look at the numbers, in 95, we already had more people on Earth than addresses. And if everybody had one address, we were screwed. By 2009, we'd already exceeded IP4's capacity. And by 2020, we're estimating roughly 75 billion internet-connected devices. So we're screwed. Well, then we came up with this little idea, NAT. Basically, what we can do is we can share a single IP amongst multiple IP systems behind it. So if we can see A, B, and C on the left here, they're using private IP space. They're behind a router that has a single public address on it, and they're able to share that address. We can see here, for example, host A's source port is 2222, but when it goes through NAT, it's changed to 7777, illustrating the problem that we have if we encode data in those port fields. So that forces data into the upper layers of the OSI model. Now there is one caveat to that. I will say that application layer gateways and server load balancers and things like that are a concern. I could spend an hour on that. We're not going to go there. So if we lived in a world without NAT, we do. Introducing IPv version 6. Little historical context for if you ever have a hacker Jeopardy question. IP version 4 is not version 4, and version 6 is not version 6. It just refers to the protocol number in the IP header field. We went from 4 to 6 because somewhere in there someone created protocol number 5, and that's why we had to skip a number. Down there at the bottom is a Wikipedia article about that protocol. So IP version 6, what's the history of it? In the 90s, when it was obvious we were going to run out of version 4 addresses, an effort was initiated to replace it. 2 years later, the first experimental protocols appeared. And then in 95, the first RFC appeared, the last one happening in 2017. Some of the changes, and this is not an exhaustive list, trust me. First, our address space quadrupled from 32 bits to 128 bits. So if we compare the numbers, IP version 4, 4.3 billion addresses, to IP version 6, we now have to use exponential notation because the number is so big. That's 2 to the 128. For the math geeks, that's 3.4 times 10 to the 38. And for those of you who are not mathematically inclined, that's the number. I can't pronounce it. Just for comparison, the number of galaxies in the observable universe is 1 times 10 to the 10. The number of stars in the average galaxy is 1 times 10 to the 11, which means there are 1 billion trillion stars in the observable universe. We have more addresses than stars in the known universe. The number of grains of sand on Earth, this is my favorite one, is estimated at 7.5 times 10 to the 18. We could assign a /64 subnet to every grain of sand and have more left. Let's get to work. Next, the address format has changed. Everyone is familiar with the familiar dotted quad format. There's some examples right there. IP version 6 changes that to a 8 colon-separated hexadecimal groups. Let's take a look. If we notice as I'm going through, not all of them have 8 groups. That's because IP version 6 allows you to truncate an address if you have a bunch of zeros together. So if, for example, in the first one, we only have 5 groups, but we have a double colon. That double colon signifies we had 3 groups that were just zeros. You can do that once per IPv6 address. Next, subnetting changes. None really. It all sort of works the same, with one exception. The /64 subnet is very special in IP version 6. If we have devices like my laptop or your cell phone or TVs or anything attached to a subnet running IP version 6, the smallest recommended subnet is a /64. The reason for that is several key features expect that /64 subnet. For example, EUI64. This is essentially like the 169.254 addressing you get in an IP version 4 when you don't have a DHCP server. Each host will generate its own globally unique address based on its MAC address. There's also the neighbor discovery protocol, which has router advertisement and neighbor discovery protocols. Router advertisement is where the router tells all the hosts, this is the subnet you're on. And neighbor discovery is basically the replacement for ARP and RARP. Finally, prefix delegation. IPv4 had no concept of this. We just didn't have the number of addresses to do this. Most people got one address and that was enough. In IP version 6, this is a scalable way to assign entire subnet blocks to customers. Common way to do it is we assign a single /64 to a customer, or some are assigned shorter than /64s. For example, a former employer of mine would assign a /60 to home users. That would give them about 16/64 subnets they could use in their network. Another provider provides a /56, giving them 256 subnets that they could use. Here is prefix delegation illustrated. We see that the ISP has a prefix of their own of 2600:1/30, and each site is given a /60, and that business down there has a /52. We'll zoom in a little bit, and we see that most customers only use one of their prefix delegated subnets, but that's how it works. All right, I'm going to stop for a sec. When I talk about IPv6 to a lot of people, people will say, wait, this is not as secure as IPv4. I don't have NAT anymore. NAT was never a security feature, and if you're relying on NAT, you're doing it wrong. NAT exists purely as an address conservation tool. The thing about IPv6 is now you have globally routable addresses everywhere. It forces you to do network security properly. So you need to have the access lists, the inspection stuff in place. So nothing about version 6 prevents you from using any of the techniques we talked about earlier on. But we have a new tool that gives threat actors a new way to extract data. Let's look at the header. It's kind of spacious. There's lots of room in there. For example, we have the flow label field. It's 20 bits. This is used in IPv6 to group packets together based on commonalities. So for example, if I have a session to a web server so that the routers and everything in the path treat those packets the same, they would get the same flow label. We also have the source address and destination address, both of which are 16 bytes. That's a lot of room. We talked about how the format of IPv6's addresses are different from version 4. We use hexadecimal, and another name for hexadecimal is base 16. And you can encode data in base 16. For example, we have the word hello. In the encoded string over there, if we have it in an IPv6 packet, we have Steganography. If you don't know what Steganography is, it's simply the art of placing another message within another, one message within another. So an image within an image, text within an image, etc. So in this case, we have meet at 10 p.m. converted to hex. We install it in an IPv6 address, and it vanishes. Just to illustrate this topic, we have 3 addresses. One of them has a secret message. It's not the one that says dead beef, but you can do that. And it's the second one. But if I put those in front of any security professional or a network professional and go, I have a message hidden in here, they'll go, you're batshit crazy. It's an IPv6 address. There's nothing there. But there is. So when we do steganography, one consideration is just how much data can I hide inside something else without being discovered? And because of that /64 subnet limitation, we can put about 8 bytes of data per packet. If we use one header field. If we use 2, we can put 16 bytes, obviously. So in this case, we put it in the host address portion, and we get that 8 bytes there and there. So if I could put 8 bytes of data into the host portion of the v6 address, where do I need to send it? Gee, if we only had a spare /64 floating around, or a couple of them. Oh yeah, that's right. Thank you, ISPs. So again, here we have our /60 prefix delegation to a site. We have an unused prefix delegation subnet. So first, we begin by configuring our router. Now you need to have a router capable of routing an arbitrary prefix delegation subnet. That's typically, in this case, a Cisco router, but anything more powerful than the average D-Link or something should be able to do this. In this case, we route that prefix delegation subnet to an arbitrary host. And there's one small problem with that, though. That host has no idea what to do with those addresses. So it'll drop them, or it will generate ICMP error messages, which we call backscatter. That's a big tell to a victim that they start to see backscatter. So we have to fix this problem. So on our host, we would configure, that's what will basically happen is the packets will be dropped. We would configure a black hole route on that host. What will then happen is every packet that arrives at that host will be dropped into the ether and vanish. But we've gone through all this work. Why would we do that? We just put a packet sniffer on there and listen to every packet destined to that prefix delegation subnet. And now we just log those to a file and we've got all of our data. So let's go across the system requirements real quick of how you would set this up. So our source, first we need to have native IP version 6. You could also use tunneling if that won't trigger alarms and cause everyone to run around the building with like their hair's on fire. Transition technologies like Teredo and stuff like that are falling out of favor and much more obvious to an in-tune SOC. You'll need compression tools. Unless you're sending small messages like I just sent up here, if you're going to send like a 10 meg file, you really need to shrink it down so you're not spending weeks sending this data. You'll need format conversion tools because once you compress, it's now binary data. So we need to get it into a base 16 format. And then you need a tool like Scapy, which is a framework that allows you to craft arbitrary packets. Or you could use tools like wget and dig and just make requests to those destination addresses. The destination configuration is very similar. Again, we need to have some sort of IPv6 connectivity, a router capable of statically routing like I illustrated a few moments ago, compression tools to undo our compression, another format conversion tool to swap back from hexadecimal to binary, or whatever format you started with, and those packet capture tools like Wireshark and TCP dump. So let's send a message. I didn't anticipate being on Sunday, so anyway, welcome to CackalackyCon. Thank you all for coming. So first, we would convert that to a base 16 string. Next, we will chop that into 64-bit segments. And then associate a numerical order identifier to each of those segments so that when we receive it at the other end, we can reassemble them in the proper order. Next, we'll put each segment into the host portion of an IPv6 address and the numerical identifier in the flow label field. Sorry I changed the color, but green on white looks terrible. As we can see, we have the flow label, which matches our identifier, and our data is now embedded in the destination address. Let's go in depth. So transmitter processing, here's the in-depth way of doing this. First, we'd select our target data as a threat actor, optionally compress it to reduce our transmission time, format convert to base 16, do the data slicing and sequencing. Next, we would construct our packet using the method we just talked about there. Again, Scapy is a real good tool to use to do that. Transmit that packet and repeat for everyone in the sequence. Sorry, got a little ahead. Okay, so we do have one small problem. In the real world, none of our data is going to always end on a 64-bit segment. So we have to do padding. How would we handle a case where we're short? Well, you could put the padding at the beginning, or you could put the padding at the end. Honestly, how you do it really doesn't matter. It just needs to be deterministic and reversible. So every time you pad, it needs to be the same so that you can recognize it when you're doing your processing. It also needs to be something you can undo. So using different patterns to mark pad bytes and stuff like that, that's up to the individual who would want to implement that. Receiver processing. So on this side, we would start a packet capture, and we would just filter down for that prefix delegation target subnet. That way we're just capturing and hoovering up the data for that subnet. Once the final segment has finally arrived at our end, we would terminate the packet capture, and we would extract the flow label fields and host identifier values from each of those packets and then order them. Once that's done, we would concatenate all of the 64-bit segments together to return us to the original formatted data, convert it back from hexadecimal, and decompress if needed. Once we're done with that, we lay back in our chair, tent our fingers, and enjoy our fruits of our labor. So whenever doing any kind of theoretical attack like this, I like to look at the weaknesses and challenges. So the first weakness of this type of attack is that it's extremely traceable. Remember, we're talking about publicly routable addresses that are globally unique. For example, if you have a phone, I believe on Verizon, you have an IPv6 address. It's unique to your phone. It can be traced specifically to you. With IP4, that was a little bit harder because we shared addresses, they moved around a lot. Hurry up and wait. This is not a particularly fast way of doing things. We're only moving 8 bytes of data around at a time. You could blast this away, but it's probably going to raise some notice. Someone will notice that there's a lot of traffic on the network. But if you're going for that good APT level attack, really low, really slow, and covert, this is a way to go. Disinformation risk. So, a threat actor working against a technically adept victim could potentially poison the stream, and they wouldn't know until it was too late. Because they're just receiving the data, they have to do all the post-processing. So I could simply load malware into their exfiltration stream when they exploded at their end. Hey, I've got you. Or I can just send data to you that's garbage for eternity. That gives my guys a time to do IR on our side, alert law enforcement, and find you. Other weaknesses, protocol limitations. That flow label field is only 20 bits long. So that gives us roughly 1 million packets that we can send before that field rolls over to 0. That's about 8 megabytes. So one of the things you'd have to do as a threat actor is determine a way to track that rolling counter so that when you reassemble data at the other end, you can you get the same data back. Packet loss. This is another problem. Because we have no flow control and this is a one-way communication, we can detect packet loss in transit, but we can't really do anything about it until it's after the fact. We'd have to retransmit. So you'd end up with corrupted data. You'd have to restart and retransmit. Getting ahead of myself, sorry. Some potential detection methods. Net flow anomaly detection. So using a technology called one-to-one net flow, where we take a digest of every packet and extract the source and destination addresses and other information about it, we can then data mine that and look for patterns that look out of the ordinary. Low and slow transmission can thwart this if you make transmission gaps as sufficiently long periods of time, like 1 packet per half hour or 1 packet per hour. Again, that's that APT level low and slow stuff. That will thwart that. Full packet capture. A well-resourced victim may have the ability to capture every packet on their network and store it for a period of time. So not only can they spot you, they can reconstruct everything you've done. At this point, this is where we'd introduce encryption of the data before we transmitted it to thwart any kind of reconstruction efforts. So, can we detect this behavior? And unfortunately for all the defenders like me out there, the answer is no. Our IDS IPS tools, will they save us? Probably not. Not currently. They currently examine source and destination addresses in very crude ways, to do blacklist lookups to match to known bad IPs, and for rough filtering. And that's it. If we're embedding data in these fields, an IDS is not going to take those fields and try and decompress them and decode them and turn them into data to find patterns. If they could, it would be computationally intensive. That's a lot of processing power required to do that for every packet that goes through the network, and it's prohibitively expensive to do it. Those fancy DLP utility systems you have at your office, those will also fall over. They are not inspecting address header fields for data. They're looking strictly at the application layer. So if you're a highly regulated environment using IP version 6, this is something you should be aware of. Your DLP tools will miss this. other issues. Those full packet capture and one net flow anomaly detection systems are very expensive. Only well-resourced companies, we're talking many billions of dollars, will have the resources for a system capable of analyzing all of that data. Back to the steganography part, the rate of false positive for detecting any of this data is going to be extraordinarily high. Normal packets are going to look like they have data encrypted and encoded in them, even if they don't, because of the way the base 16 encoding works. You'll get many false positives. Additionally, this single source to many destination addresses is a very common pattern. For example, if you were to open several web pages on your machine, you're going to talk to many hosts. This mimics that type of activity. It will not stand out too much. I would like to acknowledge some people and give them some credit. These guys were also came up with something similar to this. Barrett Miller at the University of Arkansas. He wrote a paper in 2008 called Steganography and IPv6. He discussed embedding data in the source address fields. These folks, I don't have the university that they were located at, also did encryption and steganography in the source address fields of IPv6 addresses. This is a valid technique, but there are some drawbacks to it. First, these will generate a lot of noise at your source. And so a very well-tuned IDS and system like that will detect that you suddenly have a lot more machines on your network than you should. In fact, it's a pretty big giveaway that when you've got more addresses on a subnet than actual physical machines there. Okay. And that concludes it. Does anyone have any questions?
I wanted to make a suggestion regarding the retransmit issue, where if you didn't get a packet through, you'd have to find a way to get that again. You could use tools that would do forward error correction, so you kind of spread the bits over multiple packets and allow easier reconstruction on the farther end, even if you didn't get every single packet. And regarding the encryption, possible step for using encryption, the GPG tool will both encrypt and compress at the same time.
Right.
So that might be a good thing to use to kind of take care of two birds with one stone. However, I don't know if you'd be able to get the forward error correction involved with that, but if you could do all three at the same time,
you could probably put the forward error correction in afterwards.
Or before.
Yeah. Yes, sir.
Two related questions. First one is the flow label. Is that something that you can define, or is that something that is externally defined by spec?
So the flow label field you can define that. So you ask if you can manipulate that. Using the SCAPI framework I referenced, it's a tool that allows you to craft arbitrary packets. So if you wanted to test an IDS and you wanted to send traffic that would trigger it, you would use a tool like that. That allows you to change that header field to whatever value you would like.
So the second question would be I'm sitting and thinking about IDS and IPSs, a potential suggestion to manufacturers or the builders of them is for IPv6 to tag your normal traffic with something, to have a default flow label, if you would, that if something doesn't exist, then to categorize or to catalog the flow labels that come through, and then have a whitelist or blacklist of flow labels.
That is a potential. I think the risk with that is the flow label is sort of assigned per session. So if I have, for example, if I have host A and host B talking to each other on the web server of port 80, for example, that might get flagged with one flow label. But then if they initiate an SSL connection on 443, that would potentially get a different flow label. And there's no deterministic mechanism for how those are assigned. They're sort of random. Any other questions? Excellent. Thank you, everyone.